is my pleasure to be the first of a trio. I am going to set the stage for the two speakers after me, and we are going to talk about the classification of finite simple groups. This is what CFSG stands for. And I would like to begin with a warning. Because, it's relatively early in the morning, but what we're going to talk about now is tough. It's a tough, big project. It's about really deep mathematics. It's enormous in scope. Basically, I'm saying, take a breath and fasten your seatbelts, please. Because, as I said, this is really mathematically deep. It is difficult. There's lots of different techniques. I will only scratch the surface. But I'm happy to answer questions, of course. Then the project that I'm going to talk about, that we are going to talk about, is unsurveyable in many ways on several levels. And again, I will touch on that briefly. And I will also touch on why, at least to us, it's not even completely clear when this classification project began and when it ended, if it has ended, actually. There's a lot to debate there. Now, depending on whom you ask, a lot has been said about this and written about this. The classification project spans decades, generations of mathematicians, several countries, several continents even, and this is part of the unsurveyability, 10,000 pages, maybe 15,000, maybe 20,000 pages, like printed pages in articles and books, plus a lot of communication, plus unpublished stuff. As we speak, this is about to change, but this is why I thought I should give you a tiny warning that what we talk about is just enormous. Okay, as I've said already, CFSG is short for Classification of Finite Simple Groups, and I will say something about all these words, because my job is, as I understand it, to just lay a gentle foundation when it comes to the mathematics that we talk about and the theorem that we talk about and some of the people, so that Volker and Lukas can pick it up, and then you will have heard some of the things before, and we know roughly what we are talking about. And one very high-level view on the classification theorem is basically just that it tells us that a particular problem is solvable and in a sort of almost finite way, meaning that if you want to know all the finite simple groups, then you can find them all on a list that at least looks finite, in the sense that you can write a few bullet points and then you write something down. And even though within the bullet points we have infinite families, but still it looks tidy and organized. I already said this. More on this in a moment when we talk about the actual theorem. Which brings me to the mathematical context. There are some words that I would like to explain, even though I know that, of course, there is mathematical background here. Of course, I don't have to explain to you what a group is. But let's just look at some examples, also to get a feeling for the flavor of different groups that are in the world, so that we can then specify to those that we are interested in right now. Now, for example, with the group of integers, with the binary operation addition, what do we have? We have, so let me say what I consider to be the group axioms in this example. We need a set. It doesn't need to be finite. It can be infinite. We need a binary operation on the set, which means that if we combine two elements from the set, we land in the set again. That's one of the axioms already. And then we need the law of associativity, which is something that was not always included in the definition of a group for reasons that are very natural if we look at the history. Then we have the existence of an element that serves as a so-called identity element. It does nothing in the binary operation. And we have inverses with respect to the binary operation. And that's it. And this is almost nothing. And to me, it's a little miracle how with so few axioms, this vastness of theory emerges. It's so deep and so widely spread and so diverse. There's so much going on. And to me, this is this is a miracle in some way. But it also explains why groups show up in so many places all over mathematics and beyond. Now, another example, this time we have a finite number of elements. By sim3, I would like to denote the set first of permutations of the set 1 to 3, but you can take any set with 3 elements. And if we look at the set of permutations, then we get a group if we take the composition of maps as binary operation. And here we have 6 elements, 6 permutations, and we can have a slightly different interpretation. And, oh, I can give homework to people who might get bored otherwise. Let's see. So with sim3, instead of just taking the numbers 1 to 3, I can take a little triangle. And let's try and make this regular. Let's see. Roughly. In the case of the number 3, if I take a regular 3-gon, then I can have an interpretation of all the permutations of the set as symmetries of this triangle. And I get rotations and reflections. And the rotations form a normal subgroup of order 3. So we have 6 elements in total, and the rotations, 3 of them, they form a normal subgroup, which will be important later. Homework for those who get bored. What happens if we take a quadrangle instead, a square, sorry, or a 5-gon and so on? As long as it's regular, we can always take the numbers and then we can look at which permutations of the set, 1 to whatever, give symmetries and what symmetries we can realize and how far is the distance between the full set of permutations of the set and the set of symmetries of the regular n-gon with the same n. And finally, so we can play this game with 5, and instead of the full symmetric group, I would like to look at the alternating group, which consists of all those permutations that can be written as an even number of swaps, so to speak. And these form, like for all numbers n, the alternating group on the set 1 to n forms a normal subgroup of index 2 of the full symmetric group. And this gives rise to a series of finite simple groups, as we will see in a moment. So just so we have some different flavors, first we had this group with the integers, that's an infinite set underlying this. And also it's an abelian group, which means that we have the commutativity law for the binary operation, which is something that in my world makes a group less interesting. No offense. All the subgroups are normal. Okay, then for sim3 we have a finite set underlying it, and we have an interesting normal subgroup in the sense that the normal subgroup is not the trivial group and it's not the whole group. And then we have odd 5, and I didn't prove this, but it's, I would say, medium exercise for beginning group theorists to show that odd 5 does not have any normal subgroups except the identity subgroup and the whole group. And now, just for the words that I use, a group is finite if the underlying set is finite, and this is an if and only if. And a group is simple if the only normal subgroups that we find are the ones that we always have, plus the group is supposed to be non-trivial. And in the literature, this is not always stated explicitly, but I think that everyone who talks about this means this, because otherwise there would be versions of the classification of finite subgroups where the identity group would show up. And this is not how I view things, just like I think that 1 is not a prime number. But this is debatable, maybe. So for me, a simple group is a non-trivial group that has exactly 2 normal subgroups, namely the 2 normal subgroups that we always have. So the question is, what about groups that are more interesting in the sense that they have normal subgroups that are not the whole group and not the trivial group? And then how do we use these normal subgroups? One way would be to understand the group piecewise. We take the subgroup, we take a section, then we have a group structure on the section, we can study that, and if the group is finite, then for example, this gives rise to induction arguments by induction along the size of the group. Which also means that if we look at properties of groups, then there is a natural distinction between properties that behave well with respect to not just subgroups, maybe, but also subgroups, normal subgroup sections, and properties that are not so well behaved, which makes them harder to study in this inductive setup. So if we ask for a classification of finite simple groups, then what we're really asking for is the set of all the building blocks from which all finite groups can be made. And just because there is an analogy that is sometimes made that I disagree with to some extent, this is not the same as understanding prime numbers that we understand all numbers, because the analogy works one way only. Yes, we can write down a prime factor decomposition, and yes, we can decompose finite groups into their simple sections. However, with the prime numbers, if we have the decomposition, then there's only one way to get a composite number then, or the multiple, what's the word? The product, thank you. Whereas with groups, if we have simple building blocks, then usually there are many ways how we can build a finite group from them. And this is the direction where the analogy fails, I would say. Okay, here's the theorem. Every finite simple group is isomorphic term, which means it's the same in size and structure as one of the following. It could be a cyclic group of prime order. Rotations of regular n-gons, if the number of vertices is a prime number, give natural examples for these groups. So for example, for the triangle, you have a group of rotations of order 3. That's a group of prime order that is simple just because the number of elements is a prime. It doesn't even have any other interesting subgroups, not just no normal interesting subgroups. Then we have the alternating groups of degree at least 5. Below that, we have alt 4, which is not simple, and we have alt 3, which is the same as just the cyclic group of order 3. And then we have the so-called finite simple groups of Lie type. They come in two flavors, exceptional and classical. For the classical ones, you can think of matrix groups, more or less. And finally, we have the 26 sporadic simple groups. 5 of them were known very early on, and then all the others came later. And there's an expert in the room on this, namely my PhD student Atle, who's sitting right there. Let's move on now to the historical context, because this is why we're here, mainly. To me, this is where the classification begins. I will translate a little bit. This is from Otto Hörder, 1892. It says introduction, and then it says, it would be of the greatest interest if we had a survey or overview over all the simple groups that have a finite number of elements. It says operations because at that time often groups were viewed as specific groups of permutations, symmetries, operations, substitutions, whatever language you look at. There's more to come, but I just wanted to show this briefly because for me this is one possibility to define the beginning of the classification project. As we will see, this is debatable. Hörder writes about known types of simple groups in his article. He mentions groups of prime order. He knows that these are simple and that there are infinitely many. He knows about the alternating groups. He also knows about some Lie type groups. This goes back to work of Camille Jordan. And therefore, we could argue that the classification started earlier, maybe. On the other hand, there was no explicit question or invitation to do such a classification. Also, the mature groups were already known at the time, but Hörder does not mention them. Now, what about the end? To me, this is even more fascinating, because there are so many ways how we could define the end of the classification project. Maybe you noticed that when I showed you the theorem, there was no year, there was no source, no reference, there were no names. Now, why is that? We could argue that the classification project was finished when the last sporadic simple group had been, well, maybe found, maybe there was evidence for it, maybe it was conjectured, maybe it was constructed, the uniqueness was proven. All this is up for debate. Is this a reasonable endpoint of the classification project? And again, Atle can tell you a lot about that when it comes to the sporadic simple groups. What about defining the end as the moment when there is a convincing strategy how to finish it all and trust that it can be done? Is that maybe a reasonable point of time to say this is when it ended? Or what about looking at all the articles that contributed to it in the first generation and then just looking at the last one? How do we know it's the last one? And what about defining the end as a moment when someone announces that this is the end? Okay, I want to show you some little bits of evidence that we have that support one or several of the suggestions that I just made for the end. And this is where I will come to an end with my little presentation. Basically, I want to raise more questions. Here, we see, I let Ron Solomon speak, one of the people who contributed to the classification. And it begins with, we could hear the bell toll. And for me, this is really, really beautiful. I really always like to show this. And then there's a lot of technical stuff. This supports that there was a feeling of it being done when the techniques were there and there was a plan and trust that people would do it. So this supports one of my suggestions. Maybe. We also see some more names. Aschbacher is Michael Aschbacher, who is an important contributor. We see Gorenstein, that's Daniel Gorenstein. We will see this person again. Lyons. Mason, Geoff Mason, I will have an interview with him tomorrow. Hopefully this will add to the puzzle. Then there's Janko, a person who contributed with many of the techniques, but also discovered some sporadic simple groups. And then the last sentence, psychologically, the classification was over in 1976. But this is from a survey article, and we were looking for more direct sources to support this. And this is from a letter that John Alperin wrote to Walter Feind, where again we see, and this is 76, and in the middle we see, that convinces me that the ball game is over, and we see more than 10 exclamation marks. I see a lot of excitement there. And I would like to understand better where the excitement in the community came from, whether everyone was excited equally, maybe not. And then again, this supports one of my suggestions. The methods available will, in a few years, completely classify all the finite simple groups. And now, interestingly, I talked about trust. Another main contributor is John Thompson, and here we see Thompson thinks so too. The first generation proof was announced in 1981 by Daniel Gorenstein. Some people call him the CEO of the classification, or the godfather, the coach of the team, the architect. There are many names for him. Force of nature. And Michael Aschbacher, one of the contributors, felt it was finished a bit earlier even. Again, psychologically, this doesn't mean that all the publications were out, but all of this was premature, and I'm going to show you why. We found in a letter this little comment. The so-called quasi-thin group case was one of the major cases in the endgame of the classification project. And here we see in 1991, explicitly, it's not done. There's a gap. We are not done with the classification project. And it took a long time before it was finished, 2004. Then if we look at smaller gaps like missing constructions or uniqueness proofs, then 2006 should really be the end date maybe for the first generation of the classification project. And the second generation proof started right after that. I will show you a series of books in a moment. Here it is. 9 blue books and 2 brownish books, the quasi-thin case. It's 10 blue books by now, should be 12. The second generation proof will then be 12 plus 2, 14 books. Here I can name some authors. It's much more closed than the first generation, but really the first generation proof was not a proof because there were things missing. And maybe I could illustrate why it's so difficult to define the end of this classification project. And it is even debatable whether or not we have a proof. I will show you some reasons, decades of work, generations of mathematicians working on this, and they did not always speak the same language in many ways. And then there were unpublished results, there was private communication, computers were used, and the methods are varied and very deep, and not everyone wrote in an intelligible way. That's also one of the problems. We will hear more about this in the next two talks. My job was to lay the foundation, and I hope I was successful in doing that. Now, I wonder what questions or comments you might have for me. Thank you.
All right, so perhaps the first technical question, you talk about taking sections of groups. These are like sequences of sections as you go down, right? So it's like sequences of groups.
Yes, and there is a theorem that says that it doesn't matter where you start, you always get the same building blocks, even if you find them in a different ordering somehow, but you would always get the same ones with the same multiplicity.
Is in that sense that groups are factored?
Yes. So, for example, if when I talked about Sim3, you have this normal subgroup that consists of the rotations, and then you can take this normal subgroup that has order 3, and then you can look at the section that has order 2, and then you have the two building blocks, group of order 3, group of order 2. And this is already an example where from these two building blocks you can build two very different groups of order 6, namely the symmetric group Sim3 that we started with, but you could also build a cyclic group of order 6, which is very different in structure.
And the ways to bring them back together, that's classified.
No.
You know, oh.
No, that's a difficult problem.
Yeah.
Yeah. So there's theory there, but it's not completely classified, which makes it even more interesting.
So, from complete ignorance, after Holder's remark, were there people who immediately kind of jumped in and said, yes, this is a really good thing we need to do, we should be doing this, or is it just sitting there? I mean, what happens? What is the response to him?
A bit of both, I would say. In this paper, I showed the introduction of Holder looks at groups by order, and he does it up to order 200. And he comments himself that this is not a very effective way of studying groups, but they didn't have much theory. And then some people took this and took it further, like to 1,000 and even beyond. But again, there was this question of, can we do something this is smarter? And then bits of theory started to emerge, but there was not a concerted effort going on solving this classification problem. In fact, group theorists themselves comment on this in hindsight, and they say there was a phase of stagnation that lasted until about 1950 or maybe even a little bit beyond, when Richard Brauer at the ICM 1954 announced that he has some new ideas now and some new results, and that he hopes this will spark new interest. And it did.
But do you think that at the time, at Holder's time, people, I mean, there wasn't a sense, they weren't able to really conceive of actually how monumental this was going to turn out?
Oh, yeah.
Yes.
I would imagine, and unfortunately, I don't have evidence of that, but I would imagine that there was no way that people could grasp the vastness of this in both ways. So maybe some thought this is basically impossible to do, which they thought for a long time, some of them. And maybe others said, oh, maybe we know almost everything. Yeah, and it's just a matter of developing methods to actually prove that there is not more. But at the time, I don't see any evidence for anything that comes close to the machinery that was needed to actually do it.
So yes, so there wasn't enough done by that point to excite people by that statement, in a sense.
Yes, and then also I'm not even sure how widely Holder's invitation was received. That's another thing. So that's again something that we might want to know more about, and I'm happy to have suggestions, because yes, we see papers that refer to him or ideas that very clearly are linked to what he's doing, but then it's not clear to me how beyond that it would have been taken up. And it's much later that we see, for example, in textbooks that this kind of question is even discussed.
And is there a national kind of context to that as well?
I'm not sure. I would say that there's a language context. I'm not sure how much the communication would be defined in national context. That's hard for me to say. I'm sure there are people who know more about that than
anyway. But thank you. No, that was really illuminating.
Thank you. I think you were first.
Okay. I have a comment sort of on June's, and then I have a question. So I remember you showed the Holder slide 2 weeks ago. And I was telling you a little bit about this yesterday. I think this is so interesting because the definition of a group is going to be worked out on the pages of the U.S. journals. But this invitation, as you call it, has already been issued, and like a decade later, they're going to define the group and move the axioms in and out. Mm-hmm. And then what's going to happen is that they're going to be what we would consider to be sort of homework problems nowadays. The journals are going to contain these types of problems. So I think it's really interesting and exciting that this invitation for this monumental problem comes before the definition is sorted out.
Yes, he comments on this himself a little bit later in the introduction, that he is already trying to work with groups in a slightly more abstract way, that he would not always use the same specific representation as group of permutations of a specific set or something. And in hindsight, I can see a lot of relatively modern concepts already hidden there in Hölder's work. But maybe this is one of the reasons for what you just described. Depending on who is writing, they might have a very specific perception of what a group is and what its natural environment is and how we should work with it and do calculations, and it's not yet abstract in the way that we would now look at groups. Maybe this is a partial answer. Comment?
And my second question is, on the slide of John Halpern's letter to Walter Fite, it ends with the end of an era and the opening of? What is he saying the opening of?
The opening of more and new theory. I don't have the exact words, but I can look it up because we have the whole letter. Interestingly, while there was communication, like this is the end of an era and group theory is over and so on, there were fortunately some people who understood that this was indeed far from the truth and that it's the beginning of something new. But when it comes to academic lives and jobs, there was a very real impact on the lives of people who had been working in the classification project and who then were looking for jobs, but it was clear that they couldn't be hired as a classifying person. Mm-hmm. And I have talked to people who really changed paths and they went into completely different directions. That's another interesting thing about this project and the repercussions. Thank you. I have seen many more hands before.
Back to June's comments and questions. Is it possible that an understanding of the scope of the project wasn't really understood until the announcement of some of the sporadic groups, in particular the Monster, which was a very sort of public display of this process? And there had already been other sporadic groups announced or discovered before the Monster, but the use of this kind of language that's very sort of splashy created a sense that there was something really here.
That is difficult for me to answer. I think that Volker will talk a little bit about the self-perception of the group, or at least we are happy to answer more questions along this line later, maybe in more detail. The name Monster was John Conway's idea as far as I know. There were other suggestions like Friendly Giant, which would be nice because then F and G would stand for Fisher and Grice. I Fisher died before I could ask him about this, but Bob Rice is still alive, and I'm in email contact with him, and I still have some interviews set up with people who might have an opinion on that. So there's naming, there's the communication, then there were questions like, is there a super monster maybe, or a monster group between the monster and the baby monster? Things were still not finished. There was more to discover as we know now. But that's the thing. It's so difficult in hindsight. And some of the conversations I had with contributors suggest to me that it was not the same for everyone in the group, no pun intended. Some were aware of the vastness of this, and I think some were not, or to different degrees somehow. I saw another hand, but maybe we can talk a bit more in the coffee break, because I don't want to delay everything, and Lucas is the next speaker. I hope that is okay. Thank you very much. We'll talk more later.